Hello, algebra students. This lesson is going to be called Representing Exponential Growth. There is a warm-up question on the screen. This is going to help us get ready for some of the math we're doing in this lesson. Go ahead, pause this video now and try that warm-up and come back when you're ready to discuss the answers. All right. Before we jump into that warm-up question, I do want to point out the reminder over here. The midterm is at the halfway point of the class, and that halfway point is tomorrow. The midterm is going to cover everything we did in Unit 4 on functions, as well as these first 3 lessons about exponential growth. The midterm is a longer test because it covers everything we've learned so far, half of class. So if you're an in-person student, you do get the full 90 minutes to take it. And please reach out if you have any questions about the midterm. Jumping into our warm-up, this was the question I gave you. It asked you to complete the table and take advantage of any patterns you notice here. For x equals 4, the 81 has already been given to us. We are using this part right here to help us calculate these answers. So it could be helpful to figure out where the 81 and the 27 came from. The 81 would have come from 3 to the x power. Here, x is 4, so 3 to the 4th power. Remember, exponents, this does not mean 3 times 4. Exponents mean you're multiplying 3 4 times, and that does equal 81. The next one, similarly, would be 3 to the 3rd power, or 3 cubed, which gives you 27. To figure out this next one here, I need to calculate 3 squared, which means I'm multiplying 3 twice, and that gives me 9. The next one, 3 to the 1st power, that seems a little silly because it means I just have 1 3, and so that is 3. Now for this final one, a lot of people want to say, oh, 0, so the answer must be 0. But that is incorrect, which is why it talks about taking advantage of any patterns you notice. As you're filling out this table, you might notice patterns with these numbers down here. For example, any math you could do to get to go towards the right of the table, or maybe you notice some math you could do to go this way. Since I'm trying to figure out this last one here, that pattern moving from left to right might be more helpful. And that pattern to go from an 81 to a 27 to a 9 to a 3, that pattern is each time we are dividing by 3. If I was moving the other way in my table, I'd be multiplying by 3. So going the opposite direction, I'm doing the opposite math and dividing by 3. That helps me know that for this last one here, if I do 3 divided by 3, that gives me my answer. And 3 to the 0 power must equal 1. This idea of the 0 power is true in this table, but also true for anything with the 0 power. So for example, 5 to the 0 power, what would that equal? 1. You could do the same table we did above to see it's 1. 2 to the 0 power, 1. And then finally, the name of this warm-up, what is x to the 0 power? Our rule is anything to the 0 power is going to equal 1. The reason we start with this warm-up is because we're going to do some math in this lesson that involves having an exponent of 0 or having something to the 0 power. And it's going to be important that we know that anything to the 0 power equals 1. So I would include that in my notes because it's going to come back up later on. The goal of this lesson, like we said, it's called Representing Exponential Growth. The focus here is going to be on writing an equation to represent an exponential situation, and we want to be able to interpret what the parts of an exponential equation mean. The focus of this lesson here is going to be on multiplying microbes. Specifically, we've talked earlier in our very first lesson about bacteria reproducing. We're going to see that again as well in this first problem. So we've got in number 1, in a biology lab, 500 bacteria reproduce by splitting. Every hour, on the hour, each bacterium splits into 2 bacteria. And that way they're splitting is going to be important for when we do these first two parts here. In part A, our job is to write an expression to show how to find the number of bacteria after each hour listed in the table. So I'll give you an example and then have you pause the video to try the rest of the table. We've got hour 0. Remember, hour 0 means our starting point. We have 500 bacteria. That was given to me in this table. After 1 hour, I know each bacterium is splitting into 2 bacteria. So if this is splitting into 2 bacteria, that means I'm going to have a total of 1,000. When it says write an expression to show how to find the number of bacteria, means I'm not really interested in this answer here of 1,000. What I really want from you is the math. And I got 1,000 by doing 500 times 2. The idea of splitting into 2 bacteria means I'm multiplying by 2. So this multiplication problem I wrote here, that's really what I'm more focused on. I'm going to have you go ahead, try hours 2, 3, and 6. Pause this video to do those now, and then come back when you're ready to discuss. All right, for hour 2, I'm going to be taking those 500 bacteria, and they're splitting once and splitting twice. For hour 3, I'm taking those 500 bacteria, and they're splitting once, twice, 3 times. They're splitting twice for each one of those hours. When I get down to hour 6, notice there's that jump there. I'm taking the 500 bacteria, and they're splitting 1, 2, 3, 4, 5, 6. At this point, hopefully you realized multiplying by 2 again and again and again takes a long time. There is an easier way, and that easier way involves an exponent. So I could just say times 2 to the 6th power. I could do that for these other ones here. Hour 3 and hour 2 would be 2 squared and 2 cubed there. You might have also come up with some of those answers, which is totally fine. We will use those later. We had already said after hour 1, there would be 1,000. After hour 2, there would be 2,000. Hour 3, there would be 4,000. And hour 6, there would be 32,000. I had to think for a second on that one. But like we had mentioned earlier, the part that's really going to help us for B is going to be those expressions in blue. The red part isn't necessary. Once we've written out the math for a couple of these, you start to notice a pattern here. Every single one of those expressions, we are starting with 500. Well, that's coming from that starting amount of bacteria. We said there's 500 bacteria at the beginning. And every single time we are multiplying by 2. Well, that comes from the fact that it's splitting into 2 bacteria. When we said earlier, that's where that multiplying by 2 comes from. The only part that ever changes in our math is how many times we multiply by 2, and that is that exponent there. So if our goal was to write down an expression representing how many bacteria there are at hour t, we know based on that pattern, well, we're going to start with 500 every single time, and we are multiplying by 2 every single time. The only thing that changes is that exponent. For hour 2, the exponent's 2. For hour 3, the exponent's 3. Hour 6, the exponent's 6. And for hour t, the exponent is t. So if I wanted to write an equation relating n, which is going to be our number of bacteria, to t, the number of hours, I can say the number of bacteria will be equal to 500 times 2 to the t power. This equation should work for any of these answers in our table. For example, if I chose hour 1, this equation is saying the number of bacteria would be 500 times 2, and then t is my hour. So if I put hour 1 right there, this is saying, well, 2 to the first power is just 2, and 500 times 2, that is 1,000, and that would be the number of bacteria we have there. The only thing in our table we didn't really write an expression for it was that starting point. If I tried to use the equation we just wrote for hour 0, I would still have my 500 times 2, but now my hour t, would be the number 0. That looks like a 10. Let me fix that real quick. Would be an exponent 0, which is why we started our warm-up today with exponent 0. If I go to do the math, we always start with the exponents, and I know from earlier 2 to the 0 power equals 1. So it says the number of bacteria is 500 times 1, which is just 500 here. That 2 to the 0 power, you can kind of think of it as it didn't double at all. 2 to the 1 power means it's doubled once. This means it hasn't doubled at all, so it makes sense that it's equal to 500 there. The idea of this lesson is really focused on equations of exponential relationships. We want to be able to represent exponential growth, like this bacteria, with this equation here. We also want to do the opposite of this. So instead of me giving you a story and you writing an equation, we also want to be able to look at an equation and understand what the story would be. So for number 2, this is related to the math we just did, but now instead I'm giving you an equation and I'm asking you what the numbers in that equation tell us. Go ahead, pause this video now, read through the story, and answer the question on the screen. All right, for this question, I am going to scroll up a little bit and put our previous equation on the screen as well to help us out. When we are looking at this equation, there's 2 numbers, the 100 and the 3. The 100 is going to represent something similar to what our 500 represented in that last situation. The 100 is telling us the number of single-cell parasites there are at the beginning, or you could also say the number at hour 0. So our 100, we can say, is the starting amount of parasites. I'm going to put at hour 0 there. If I were to substitute 0 for hour t, if I were to put a 0 right there as the exponent, it would equal 100, because at hour 0, at the starting point, there are 100 parasites. The other number we have here, the 3, is going to be similar to what that 2 was. Remember, the 2 was telling us every hour the bacterium splits into 2 bacteria. Here, the 3 is telling us that rate our parasites are growing at. I don't know too much about parasites, so I don't know if they split, but I can use that word we had seen in a previous lesson. I can say they are tripling. So I can say the 3 tells me that the number of parasites triples. I don't want to stop there, because does it triple just once? Does it triple every second? I need to think about how often it does it, and it's going to the number of parasites triples every hour. So if I go from hour 0 to hour 1, I've multiplied by 3 because that's tripling every hour. And remember, that word triple means you're multiplying by 3. So I like these 2 questions because we get to practice going both ways. Me giving you a story and you writing an equation, or me writing an equation and you putting together what the story was. Both of these here, what we are focused on is the growth factor. Those are one of the 2 things we need to write and understand the equations. And the growth factor, I'm going to point out what it was in these 2 equations first. In this first equation we wrote, the growth factor was the 2. And in this second equation here, the growth factor was the 3. It's just telling us what the name sounds like, right? It tells us how quickly it grows. And we're calling it the growth factor because we've talked about how that word factor means you're using multiplication. It's telling us what number we're multiplying it by. So here's our definition. In an exponential function, the output is multiplied by the same factor every time the input increases by 1. To give you like a concrete example with that sentence there, this would be saying that our output, the number of parasites, is multiplied by 3. When it says the input increases by 1, that just means each 1 hour, right? So the number of parasites is multiplied by 3 for every 1 hour. The growth factor is always going to be the multiplier, that number you're multiplying by. In almost all of the examples we have done so far in this unit, we've done a lot where maybe you are doubling something and you're multiplying by 2, or you are tripling something and multiplying by 3. We start with a lot of those situations because those words double and triple are most familiar. But please note, your growth factor can be any number. You can have bacteria where every hour it multiplies by 1.5. You can have decimals and fractions for your growth factor, or you can have something where it multiplies by 10 every hour. I know during the pandemic, they thought that was the rate the COVID virus was spreading, right? And we talked about the growth factor a lot during the pandemic to figure out how quickly it was spreading. So that growth factor can be any number. It doesn't just have to be doubling or tripling. The second part to this lesson is we're continuing with microbes, the bacteria, and the parasites. But this time we're going to be focusing in on graphing them. So this is the table we had created earlier for that first story about the bacteria. And using that table we created, we are going to go ahead and graph that equation. So earlier when we were making that table, we were talking about our T and the number of bacteria there were. So we had said at hour 0, remember we were starting with 500 bacteria and it was splitting into 2 each hour. So after 1 hour, there was 1,000 bacteria. After 2 hours, there was 2,000. The directions say we're going to graph it when T is 0, 1, 2, 3, and 4. So hour 3 was 4,000. That was in our table. Hour 4 wasn't, but I can calculate that pretty easily. I know it's doubling or multiplying by 2 each time. So 4,000 multiplied by 2 gives me 8,000. I'm going to go ahead and graph these numbers over here. And notice it says here, and on our graph, my T is my horizontal axis or my x-axis, and then N is my vertical axis or my y-axis. So when I go to graph this first point at hour 0, we have 500 bacteria. That's going to be halfway to 1,000, so I'm going to put it right here. At hour 1, we are at 1,000, so that's easy enough to graph. Hour 2, we are at 2,000. I can find that line for 2,000. Hour 3, we are at 4,000. I'm going to make sure I go up and not sideways and right here. And then finally, hour 4, we are at 8,000. Right there. Okay. And so we have this graph here. Now, if you remember from the Gini situation, we had talked about what graphs of these exponential equations look like. We didn't see any in last lesson, but we're seeing it here again. Notice I'm getting that curved line a little bit, and I can even connect these to help emphasize how it's curving there. Because it's curving, I know it is not a linear function. Linear would be growing by the same amount. And here I'm seeing I'm not increasing by the same amount. Here I went up 500, I went up 1,000, I went up 2,000. But what I am going up by is a constant factor each time I'm multiplying by 2. And if you see that common factor, that growth factor, now we know what it's called, where you're multiplying by 2 each time, that is how you know that it is exponential. Each time we are doubling to get to the total number of bacteria. Now I went ahead and I graphed this first equation here. The second graph we're going to do is for the other one. So this was the parasite example we had come up with. Again, my suggestion is to create a table like we did above to help you graph. Go ahead, pause this video, create your table to help you graph this situation, and then come back so we can discuss it. All right, I've got the table here and I did show my work so you can see how I calculated each of those numbers. For me, I just kept tripling the number from before, but you could have also used this equation to help you get to those numbers. I did let you get to try the more fun graph here. So we didn't have lines for any of these numbers, so we had to do some estimating. For example, 900 I know is going to be a little below the 1000. For 2,700, I know that middle line is 2,500, and then the next line would be 2,750. So I know it's pretty close to that line there. So you get to practice some estimating. But we get this graph here. It is also curved like the one before because this is also an exponential function. I know that because I'm given this equation here, and I see there is a variable as an exponent. So that helps me know that it is an exponential function. And so we've got similar to before that it's curving. It didn't increase much at the beginning, but then by the end, you're definitely getting a lot more parasites from hour 3 to hour 4. Thinking about these graphs, I want to connect the graphs to the equations we had been looking at. And so starting with that first one again, this was the one about the bacteria. When we are looking at this graph here, each of these numbers, you can find a connection between the equation and the graph. So first, that number 500, where can you see the meaning of 500 on this graph? Well, remember the 500 we had talked about was that starting number of bacteria, and so I see it on my vertical axis. It's right here as my vertical intercept. And it is showing up as my vertical intercept because it's the starting point. It's telling me at hour 0, we are starting with 500 bacteria. That is always going to be true for every single exponential function. When you're looking at the graph, this number right here is going to represent that vertical intercept or your y-intercept. The 2 might be a little harder to find. When we talk about finding 2 on the graph, I'm not talking about here's the number 2, but connecting the meaning of the 2 in the equation to where it would show up on the graph. It helps to remember where that 2 came from. So we remember we said it was doubling every hour or splitting into 2 every hour. And so you see that 2 when you look at the numbers and how we get from one to the next one. So for example, this point here is at the number 1,000, and this one is at 2,000. So to get from 1,000 to 2,000, we had to multiply by 2. That next point is at 4,000. So to get from 2,000 to 4,000, we had to multiply by 2. To get from 4,000 to 8,000, we had to multiply by 2. And so that multiplication and that 2 right there is our growth factor, which I'm seeing when I look at those y coordinates, or here I guess those n coordinates, and how we get from one to the next one. That would also be the same thing for that other equation we had looked at. My 100 right here would be my y-intercept or my vertical intercept. And then my 3 is my growth factor as well. It's that number we're multiplying to get from one to the next one. The final thing I want to do with these 2 graphs is put them both on the screen here and do some comparing. If you were comparing these 2, how would you compare them? Do you have any observations looking at both graphs? Go ahead, pause the video if you need to take as long as you want and see if there's anything you notice comparing these 2 graphs. Some of the things I've heard in class in the past when we've compared these is related to the 2 main features we were just looking at. First, I've had some students point out that the second one, which real quick, just as a reminder, this one was the one about bacteria, where we started with 500 and we were doubling each, or I should use their variables. Oh, I was doing it right. Every hour, which we were saying was t. And then this was our parasites, which we said started with 100, and it was tripling every hour for t. So one of the things I've had people point out in the past is the parasites, we're starting out with less of them than we do with the bacteria. So to connect that to our equation, our bacteria we know is starting at 500. Our parasites we see are starting at 100, so it's starting a little lower on that y-axis. The other thing sometimes students mention is how they're growing. So if you look at the curve of each of these lines here, some people notice that the second graph, it's growing more quickly. And you can put some numbers to that even. We had just said the parasites start off a lot less than the bacteria, but by hour 4, remember this last point here was 8,100, and this is only 8,000. So we're seeing this one here grows more quickly. There's a reason for that, and it is because of the growth factor. If you're multiplying something by 3, it's going to grow more quickly than something that's multiplying by 2. So for example, if I had 2 equations to represent 2, let's talk about bacteria, I guess. And one of my equations looked like this, and then my other equation looked like this. And I said equation, so I guess I should say the bacteria. If I asked you which one of these is growing more quickly, do you have an idea? Well, to know which one's growing more quickly, I'm looking at that growth factor. So I'm comparing these numbers. And so this one here would be the one that grows quicker. I know that because 5 is greater than 1.2. And a different question, if I had asked you which one of these is starting with more bacteria, well, that's going to be this one because 1,000 is more than 5. This one here is starting with more. Both of these would still be exponential. I know that because they have a variable as an exponent. So they would still be a curved line. Just the one that's growing quicker, it's going to start looking more vertical a lot quicker than something that isn't growing as quickly. So to summarize, there's 2 key takeaways from this activity with the graphs. And that is, what does the vertical intercept tell us? And what does the growth factor tell us? You can answer these questions. It means you understand this lesson. So for that first part, what does the vertical intercept tell us? Well, the vertical intercept of the graph is the initial bacteria population size, or the starting amount for whatever the story is about. It is going to be in the bacteria story. It's the size of the population when first measured, or which oftentimes we refer to as hour 0. And then what does the growth factor tell us? The growth factor tells us how quickly the population increases. Remember, that's that number that you're constantly multiplying by. This is the end of this lesson on representing exponential growth. Thank you so much for watching. I hope you found it helpful, and I'll see you in the next one. Bye, y'all.